My dear student, colleagues, and all the viewers who are watching this program live from Facebook page, Physics Adda, I'd like to welcome you all to our International Physics webinar. And today it's our 51st International Physics webinar. So good afternoon to all. So hope you are well and safe from Corona pandemic. And all you know that we are staying in a Corona pandemic situation. So we cannot continue our academic program inside the campus. So we have to start our online program to continue our academic program. So our Department of Physics, Pabna University of Science and Technology has started some online program, including online classes and online international physics webinar. And we have successfully completed our 50th international physics webinar. So today is our 51st. So, and we are going to adjust with this new normal, and we are trying our best to adjust with this new normal. Today, I'd like to welcome you all to a joint session between Pabna University of Science and Technology and the Department of Astrophysics and Cosmology, Bose National Center for Basic Science, Kolkata, India, in Astrophysics and Cosmology. And we have with us here today Dr. Archan S. Majumdar, Senior Professor and Dean Faculty, Department of Astrophysics and Cosmology, Bose National Center for Basic Science, Kolkata, India, connecting us from India. So he has already connected. So I'd like to welcome our speaker. So good afternoon, sir.
Good afternoon. Good afternoon.
And welcome to our International Physics webinar, and welcome to our university in Bangladesh. So
thank you so much. Thank you.
This will be a great webinar with you, and I think our student will be benefited with this webinar. So we have already arranged a series of webinars, and in those webinars, the physicists from different countries are coming as a main speaker, and they are delivering their speech. They are sharing their knowledge with our student, and I think by this way, our students are benefited. So the main aim of our International Physics webinar is to motivate and encourage our students in this Corona pandemic situation, and I'm happy of doing this. So today, actually, we'll do a 51st hour webinar, and our speaker, Dr. Archan Majumdar, Senior Professor and Dean, will talk about, I think you have already come to know the title of our today's webinar, Introduction of Quantum Information Science. So for those who are new, I'd like to introduce that we have divided our webinar into 3 parts. First of all, I'd like to introduce our speaker with all of you, and then our speaker will deliver his speech, and at the end we have a discussion time. In that time, anybody can join. So I think you have already come. The title of our today's webinar, an Introduction to Quantum Information, and the speaker is Dr. Archan S. Majumdar, Senior Professor and Dean Faculty, Department of Astrophysics and Cosmology, Bose National Center for Basic Science, Kolkata, India. So if we see his educational background, you can see he has completed his master's and PhD degree both from University of Delhi, and his professional background, he has more than 100 peer-reviewed international journal, and about 50 invited talks in school, conference, and workshop, and about 12 PhD students have completed already, and course offer on quantum theory and cosmology, and organizes 6 international conferences and delivered lectures in 15 outreach program. And if we see his research interests, so quantum information and foundation, quantum correlation theory and application, quantum non-locality, measurement problem and decoherence, and general relativity and cosmology, dark energy problem from different perspectives, primordial black holes, and the gravitational wave spectrum. And you can see his significant recent publication, and this is his Google Scholar ID. We can see his citation number is more than 2,400. So thanks for all of your patience. So now we can go to our today's speaker. So thanks, sir, again for accepting our invitation, and it's your time. You can start your session, sir.
So thank you very much. Sorry, you were saying something?
I would like to say thanks on the behalf of the Department of Physics, Pabna University of Science and Technology, for accepting our invitation. Thanks, sir. You can carry on.
Okay, so Dr. Das, thank you so much for this invitation, and I would like to welcome all the audience. and it is a great occasion to be able to connect with you online. So this is a very good initiative which is being organized by Pabna University, and I'm very happy to be a part of you. And at the moment, I mean, of course, online, but hopefully sometime in the future, we can have some physical contact when this pandemic is over. Yeah. So you can come here, people from your side can visit here, and of course, people from our side, including me, would love to visit there too. So, of course, I am again very pleased to deliver a talk which is organized by Pabna University because of one more reason. Actually, Pabna is a place from where my ancestors came. So this was many years ago. So more than 5 generations ago. But still, there's some kind of sentimental attraction for me to be able to deliver a talk at Pabna. But today, I think I'm very glad I've seen your web page and profiles that Pabna University is starting a very good work. There are active researchers there. So thank you again so much. So let me now go to my formal talk. So I will do a slideshow. I am hopeful that this is visible to all of you. Yes?
Yeah, it's okay, sir. We can see.
Okay. So let me start my formal talk. So the topic of today's talk is an introduction to quantum information science. And as Dr. Das has very kindly given this introduction, that my name is Archan Majumdar. I work at the Satyendra Nath Bose National Center for Basic Sciences in Kolkata, India. Of course, the name of Satyendra Nath Bose actually connects our two lands, both, I mean, what is today called West Bengal and what was earlier East Bengal, because before 1947, Satyendra Nath Bose also spent, some very great time at Dhaka University, and he did some great works from Dhaka University. So this actually, Satyendra Nath Bose is a physicist without a nationality, so he connects both our lands together. So presently, I work at the SN Bose National Center for Basic Sciences, Kolkata, and I also should mention that many of your students from Bangladesh know or should know that indeed in Dhaka University there exists also an SN Bose Center, which I have had the privilege of visiting a few years ago. So again, this calls for a very fruitful interaction on our sides. Okay, so this topic of quantum information, why is it important today? So this is one of the most challenging topics of the present generation in physics, and also a very interdisciplinary topic in physics. And why I should say not only physics, but this topic attracts very bright minds from not only physics, but many different branches of other domains, for example, computer science, theoretical chemistry, and even biology. So this is a very interdisciplinary topic. And why is this topic become so popular nowadays? Of course, those of you who are physics or science students know that quantum mechanics is one of the founding pillars of modern physics. But quantum mechanics was discovered more than a century ago. In fact, most of the important works on quantum mechanics happened in the early 1900s, that is the early 20th century. And among them, I mean, if you can ask what are the two very, important works or founding pillars of quantum mechanics, I mean, every student knows. This is the uncertainty principle and superposition principle. So these are two things, the uncertainty principle and the superposition principle, which actually makes quantum mechanics very different from classical theory of physics. So all that we have learned in classical physics, for example, starting from Newton's law, they undergo a paradigm shift when we go to quantum mechanics. And this paradigm shift was discovered in early 1900s with the pioneering efforts of great physics minds, starting from Albert Einstein, Niels Bohr, Erwin Schrödinger, Werner Heisenberg, Max Born, so on and so forth, Paul Dirac, so on and so forth. So this happened in the early part of the 20th century, and very rightly it is called the first quantum revolution, because in the mid-20th century, this brought us many, wonderful new technologies, starting from transistors, lasers, etc. And all of you know that we use these technologies, and this would not have been possible unless quantum mechanics was discovered. So that was the situation till about 30 years ago. And then finally, in the 1990s, again, something very wonderful and very fascinating happened. So people are all over the time, right from the start of the 20th century, there were certain key questions in quantum mechanics which people did not understand. So these were quantum foundational questions raised to quantum measurement problem. I will come to that in the talk. Quantum measurement problem, quantum entanglement, quantum non-locality, etc. People did not understand these things, and a deep study on these things led to the discovery of quantum information science. So that is from one side, deep studies of several issues in quantum physics, quantum mechanics, and also developments in classical information theory. For example, there is the pioneering work of Shannon information. So both of these things came together in an interdisciplinary effort, and in 1990s, this subject of quantum information science has developed. Okay, so now this subject actually brings us a fascinating potential for entirely new kinds of technologies, so we have not even heard so far. Okay, and I think all of the students may have heard about a few names, if not, I mean, a lot of things, but at least I think you have heard about quantum teleportation, you have heard about quantum cryptography, you have heard about quantum computation. So these things are quantum communication. So these things, even when they are accomplished at the practical level, of course, there are demonstrations today, but when they really come to the technology market, this will actually completely revolutionize the way we basically conduct our lives and the way we basically think about scientific issues. So this has indeed ushered in a second quantum revolution in the last 25 to 30 years. Okay. So in this talk, I would like to give you a brief flavor of this topic, of course, which is a very large topic, as I've said, but I would like to motivate you and give you a brief flavor of this topic. And why I'm doing this? Because the only purpose is that more and more young people should try to actually study and take up this topic, because in the future, it will be extremely important. Among the many different areas of physics, this is one of the great areas for a very bright future potential. And I should not say just future potential. Even at the present day, if you look into major developed countries in the West, and not only West, some countries in the East also, including our neighbors, who have made tremendous progress in this area, and new quantum communication technology is going to completely revolutionize our thinking, our way of life. So this is the right time for young minds, young students, whether they come from physics, whether they come from mathematics, computer science, or whatever, to actually try to understand and learn this topic. Okay. So during today's talk, I will first give you a brief historical background, how this subject developed, because this is key to understand the following developments. So I will definitely talk of some historical backgrounds. And in talking of historical backgrounds, of course, the subject of quantum foundations will come up. So quantum foundations, most of you are young people, so probably you do not know that much of history of quantum foundations, but at least I should just mention that when I was a student, it's more than 30 years ago, this subject of quantum foundations, people did not used to pay much attention to it. And whenever somebody used to ask a question regarding quantum foundations to some professor, I mean many old professors, they used to say that, oh, why do you want to do this subject? This is subject only for people with gray hair. So you forget about it. First you do your research, have a job, and then settle down. And when you will retire, you bother about this subject of quantum foundations. But unfortunately for them, or fortunately for the whole world, actually some very key and fascinating developments took place in the last 30 years. And nowadays, not only people, young minds in many physics departments all over the world, in universities, institutes are bothering about quantum foundations. So this sort of a taboo of or mystery of quantum foundations is some way getting solved. Okay. So after having talked of the historical background and quantum foundations, I would move to the heart of this subject, that is heart of quantum information theory, and that is nothing but quantum entanglement. So I would try to explain to you what is quantum entanglement and why is it on the one hand so mysterious and difficult to understand, and also on the other hand, why is it so important for modern quantum information science and technology. So this is roughly the plan of my talk, and I will appreciate if many young people, at least several of them, note some questions during the talk, and I will be happy to give answers and discuss with you after my presentation. Okay. So the basic thing, as I said at the beginning, that the whole paradigm shifted once in the early 20th century when we went from classical physics, Newtonian physics to quantum physics. Okay. So, and again, I mean, lot of you people at the undergraduate level, and these days, I mean, even at the school level, you understand, you know about these basic developments. For example, if you have a classical particle and you try to plot its trajectory, starting, say, in the x versus time or the yx configuration space, whichever you like. So for a classical particle, it starts from an initial point with well-defined coordinates and it reaches a final point, and the trajectory is well-defined. Okay, it is along a straight line, depending on what kind of geometry you are using. But when you go to the realm of the quantum particle, first of all, you cannot specify the position and momentum both of a quantum particle with complete accuracy, even in the initial case. And of course, you can get a final state for the particle, but the trajectory is not well defined. In fact, between 2 points in phase configuration space, there can be infinitely many possible trajectories. So this is a clear difference between your thinking of classical mechanics and your thinking of quantum mechanics. Now, in this small table, I have just listed for you, those of you who have done at least some basic studies in quantum mechanics, initial studies will come to immediately appreciate this table. For example, if you talk of position of a particle, in both for a classical and for a quantum particle, you can label it by the coordinate position, say x. Okay. However, the function, the function which can depend on only position for a classical variable, it takes the shape of an operator in quantum mechanics. So, in quantum mechanics, you can have an operator, maybe a position operator, and this position operator you will have to apply it on a quantum state given by the wave function. Then only you will be able to obtain a expectation value or an eigenvalue for position. So it is not as straightforward as in classical mechanics. And similarly for momentum, P is a classical variable for a classical particle. However, in quantum mechanics, this momentum is replaced by the quantum momentum. And as you can see, this h cross Planck's constant comes in. Also the iota imaginary square root of -1 comes in, and this is just the derivative of the position operator, and similarly for energy. So at this stage, this was just a summary to actually focus your mind on quantum mechanics, what we were doing. But how did this fascinating theory develop? Okay, so it has a nice, interesting history. Okay, so what is basically quantum theory? So quantum theory is nothing but a description of the way of small particles. Okay, and indeed, if you think our whole universe is made of small particles. At the elementary level, what do we have? In fact, you are probably sitting in your chair or in front of your computer or a table or wherever, and you are sitting in front of classical objects. But if you can imagine, just try to think, what are the big classical objects made of? They are made up of nothing but molecules and atoms, and even at a final level, subatomic particles. So if we have to understand physics properly, we have to understand physics of small particles, and quantum mechanics is nothing but the properties or physics of small particles. And indeed, what we have learned from quantum mechanics is that physics or their behavior of larger objects is very different from the behavior of small objects. So all of us are intuitively familiar with behavior of large objects, but quantum theory, whenever we come to the microscopic level, it can be completely counterintuitive. And you know many examples. So again, historically, let us start with the behavior of light. Okay, so what is light? Light, we know, has spectra. So white light, for example, is built up of several colors. And in the 17th century, if we go back 300 years, Newton tried to analyze this problem. Suppose I shine some white light on a prism, and on the other side, this light actually divides up into various colors. So Newton came up with the idea, that was 300 years ago, that light is made of particles, and particles represent the color, and therefore upon reflection or refraction from a prism, the different colored particles follow different trajectories. Okay, and this was the postulate of Newton. However, later on, people observed that light, however, just does not behave like particles, but behaves more like waves. For example, 1803, Thomas Young did his famous double slit experiment. What is this double slit experiment? There is a light source and light comes out from the source, and some distance away there is a screen, and inside on the screen there are two gaps or two slits. One is here and the other is here, and on this side of the screen, if you look, you will see interference patterns. And previously, before this time, people were familiar with interference patterns caused by waves. But what kind of waves? For example, water waves, and also, for example, sound waves. Of course, sound waves you cannot see, but you can feel their effect in many different ways. So interference was noted to be a wave phenomena, and now since light is exhibiting a wave phenomena, so after this Young's double slit experiment, it was generally accepted that light is made of waves rather than particles, right? Okay, but then came the year 1905, and Einstein did his famous experiment on photoelectric effect. And what did he do basically? So this is a metal plate, and light was shown on this metal plate. So light is falling on this metal plate, and then due to the falling of light, some electrons are emitted. So you know all metals have free electrons, and the action of this light means the energy carried by the light actually liberates some free electrons. And why did Einstein say that this is the particle character of light? Because what is observed is a certain amount of energy was required to dislodge an electron. So people used to may have expected that the more the bright the light is, and if a certain threshold of brightness is reached, the electron would be released. However, contrary to that, what was found in this experiment, that brightness made no difference whatsoever. What indeed mattered was the color of the light. So for example, even very dim blue light would release electrons. However, if you shine very bright red light, electrons would not be released. Now, all of you know what is the color of light has to do. Color of light has to do with the energy of light by the Planck's law. E equal to energy equal to Planck's constant times frequency, or 1 by wavelength. Okay, so this clearly said that light is made, this actually proved light is made of particles of different color, in fact in the way as somewhat in the way as Newton had suggested. So blue colors had shorter wavelengths, means higher frequency, therefore they had higher energy. So energy of the photon is proportional to frequency, and this constant is called the Planck's constant. So we come up with a situation where light can behave both like a wave and like a particle. Okay, so this is a cartoon which said that each quantum light is a quantum character, and each quantum consisted of a fixed amount of energy. So then immediately people used to have bothered about this, that light can either behave as a particle or as a wave. So this phenomena is called wave-particle duality. Okay, and this is intimately connected to the principle of complementarity. And what does complementarity tell us? It tells us that in any given experiment, if you choose any particular experimental setting, light can either behave as a particle or can behave as a wave. It cannot both simultaneously behave as particle and wave, but in different experimental setting, it can behave either as a wave or as a particle. Okay. So this feature which I have told you about light is not only valid for light, but it is valid for any quantum mechanical particle. So what is the statement? A system can exhibit wave-like behavior and particle-like behavior, but no experiment could demonstrate both behaviors simultaneously. So this is a fundamental characteristic at the level of quantum particles or small particles. Okay, so for example, just like light, even matter means atoms, small atoms, electrons, protons, or whatever, neutrons, they behave like particles, and they have a characteristic wavelength which is extremely small, because you have the H Planck's constant in the numerator and the momentum in the denominator. Okay. So, and then slowly, soon afterwards, Schrodinger gave his equation, which is called the Schrodinger equation, and which tells us actually what is the dynamics of a quantum particle. So, if the particle has a given quantum state, which is represented by this psi wave function, which is a function of its coordinate and time, then you can find the time evolution of the state, which depends on the potential that is there, V, and of course this D'Alembert. Okay. So this model can actually place quantum mechanics on a very firm mathematical setting, and indeed when it was discovered, it turned out to be one of the most accurate theories of physics ever invented. Okay, the experimental result, the experimental forecast which were made by applying this theory turned out to be extremely accurate one when one does the real experiments. Okay. So as I said, so quantum mechanics, a quantum particle can behave both like a wave or a particle, and indeed you can have similar experiments of superposition and interference using not just photons but also electrons as well. So if you look in this side of the screen, so there are electrons here which fall on the screen. There are two slits on the screen, and on the other side, if you place another screen, which is an optical screen which is far away from this screen, then after a long time you will see collections or dots which have accumulated representing hits of electrons on the screen, and they accumulate in such a way that there is a clear interference pattern. So at this stage, for example, there are lots of hits, whereas in this space there is no hits, smaller hits. Okay, so on and so forth. So this can be actually represented by this sort of modulated interference pattern. Now, then the next question is, suppose I say that instead of sending too many electrons together, suppose I send one electron at a time. I send one electron and let it pass through this hole, either of this hole or this hole, and fall on the screen. And then I wait, then I send another electron, so on and so forth. Now, let us say I do this, repeat this experiment 1,000 times, 5,000 times, 10,000 times. Afterwards, again, what you will find is a similar accumulation, right? With a similar interference pattern. So now, what does this tells us? Of course, when there is only one electron in the picture, it does not know that another electron will come behind it. So in this way, the electron is interfering with itself. So the wave function of the electron, which has a finite possibility of passing through either the upper slit or the lower slit, that is interfering with all its possible paths. So therefore, this is called the superposition of a single particle with itself. Okay, so now this problem also gives rise to some fascinating questions. So as I just asked you, as I just raised this question, when a single electron passes through this hole, I mean, and you know that the electron is a quantum particle, so it will obey Bose's complementarity principle, which tells us that a given quantum particle at any instance can behave either like a particle or like a wave. But when the one electron is passing through one of the slits, how can it decide whether it wants to behave like a particle or a wave? Okay, so my question should be clear. So the point is that what makes the electron decide whether it will behave like a particle or a wave? Of course, an experimenter knows which property the experimenter will like to actually measure. For example, if the experimenter wants to measure the particle property of an electron, then what he or she will do, he will place a detector. So this is again the same diagram on the right side. So there is electrons maybe coming one at a time, falling on this screen. So suppose I want to find out the particle property of the electron, I will place a detector here, and if it came out of this slit, of course, this detector will click. And if it clicks, then what do I know? I know, first of all, that this is a particle because it fell on a detector, and I also know that this came from this window, this slit. Why? Because its probability coming from the lower slit is extremely small. Okay, it has to come all the way down and all the way up. So most probably it will come from this slit. Similarly, if I place a detector near this slit, very close to this slit here, then if this detector clicks, then I know for certain that the electron is a particle which had followed a definite trajectory. That is, it has followed the trajectory of coming through this slit, not the slit above, right? So, and if I do not want to measure the particle property, I want to measure the wave property, then I remove both these detectors and I just place the optical screen. And after many electrons have passed through one at a time, then I indeed obtain a interference pattern on the screen. So, okay, so one can obtain either interference pattern, wave nature, or which way information, that is particle nature. Particle nature will tell me which way, either through this way, lower slit, or through the upper slit, by introducing detector in front of the slits. Okay, so I can introduce the detector. Now again comes a very baffling mystery, is that now this choice, so this you all of you agree that this is the choice of the experimenter, whether the experimenter wants to insert a detector or whether the experimenter does not want to insert a detector. So now this choice of the experimenter can be delayed, right? It can be postponed. And what I mean here is that I can so arrange that the electron actually passes this slit, and only after that I can insert a detector here, right? So you understand what question I'm asking? I'm asking is that when the electron actually passes this slit, one of these two slits, it does not know whether it will face a detector at the end or whether it will face a screen. So again, the same question, how will the electron decide whether it is to behave like a particle or to behave like a wave? So in fact, this famous question was asked by John Wheeler in 1978. And Wheeler, by the way, for those of you young students who do not know, is a famous gravitational physicist, and he also wrote a very large encyclopedic volume on general theory of relativity, which is there, which should be there in many libraries. But he was also interested in foundational problems of quantum mechanics, and he posed this question whether it is possible to make this delayed choice experiment, and under this delayed choice experiment, can we know for sure that whether an unabsorbed electron or atom or a photon is a particle or a wave? Can we know for sure? So that question Wheeler asked in 1978, and of course in 1978 the technology was not so developed to actually do this experiment practically, but after 30 years, in the year 2007, indeed the technology improved so much that Jacques et al. Did this real experiment, and this was published in the famous international magazine Science in 2007, where they could clearly come to this conclusion that no such inference of particle or wave nature can be reached for any quantum particle until and unless it is able to interact with all the available setup that is possible. So just by making a delayed choice, you cannot force, you cannot know whether the atom or electron behaves like a particle or a wave at any intermediate stage of the experiment. You can only be sure at the end of the experiment. So this is a very nice experiment, and the details, if anybody is interested, I will go into at the end of this talk. Okay, so far, this is a brief historical introduction, and for the purpose of our talk, then what is most relevant is that these two possibilities, for example, passing through the upper slit or lower slit, can be labeled by two dichotomic variables. Okay, so for example, I can name the possibility that the electron or atom or photon has passed through the upper slit by the symbol 0, and I can label a similar possibility of passing through the lower slit by the symbol 1, and then I can combine these possibilities in the manner of superposition. For example, 0 plus 1, 0 minus 1, and not only that, I can add any given phase, any given complex phase in front of these possibilities or probability amplitudes, probability densities. So these are nothing but probability densities, and I can construct infinite superpositions, just that is possible to do through the Schrodinger equation. So therefore, this brings us to the question of information. So nowadays, all of you students are aware of these things, bits, okay? So I assume that you know what a bit is. So classical bit can take two values, either 0 or 1. So what happens in quantum mechanics? Of course, in quantum mechanics, you just imagine that you have a surface of a two-dimensional sphere. And you just don't imagine, of course, this as a physical basis, because if you take a spin of a spin half particle along a certain direction, then all the values lie on the surface of this two-dimensional sphere. Not only spin of a spin half particle, but if you also take the polarization of a photon, you can have two polarizations, horizontal and vertical, and all the combinations of these two polarizations lie on surface of this two-dimensional sphere. So, for example, you not only have this bit 0 pointing this way and this bit 1, let us say, pointing this way, but you can construct a superposition 0 plus 1, and it is normalized, of course, by bit 2, and it is clear why you need this normalization to conserve probabilities in quantum mechanics. So you can build up, as you see from the surface of the sphere, you can build up infinitely many possible values and on these surfaces. So just starting from these two building blocks, you can build up infinitely many possible combinations. And therefore, using this property of superposition and another property of entanglement starting from the 1990s, this has actually ushered in a potential of immense quantum technologies. Okay, so what does it happen? So before I talk of quantum information, let me just try to remind you basically what is information, right? So when the word information, when you hear the word information, what does strike your mind? Of course, nowadays all of you are on social media every day, from morning to night. You come across all kinds of information, some good information, some not so good, some very useful information, some very fake information. But if you just try to think, just imagine what is information. Just maybe for one moment try to think in an old-fashioned way. So if you go into a library, old-fashioned library, you have a collection of books there, and for example, you open any book and try to open one of its page, and on that page, what do you think? What you see is something which is typed there, right? So type some sentences typed there. For example, in an encyclopedia, one of the first things that is typed is A, and maybe a word for A, apple, and then this goes on to describe what that apple is. Apple is some kind of a fruit which has this properties, right? So this is some kind of information. Now try to think more deeply. After all, how is this information coming to you? This information you are reading from a page of a book, and on the page something is typed. So what is the typing after all? So typing means that there is some stable permanent ink which is putting some pattern on the page, right? Of course, it is put in form of a language so that you can understand, but after all, it is some pattern of ink. Now, think slightly more deeply. So what is this ink after all? Ink is made of a collection of particles, and what are these particles? They are molecules and atoms, nothing else. So now, if you want to try to understand the physical character of information, then you will have to understand the physical character of how the information comes to you. In this case, information comes to you through ink patterns. And in the end, if you look deeply enough, it is nothing but a pattern of molecules. And of course, whenever you want to describe physical property of molecules, you have to apply quantum mechanics. So there is no way out. So the whole message of this slide is that information is encoded in the state of a physical system, right? And after all, information ultimately is encoded in the state of a quantum system. Nothing more, nothing less. Okay. So now just with this kind of information, you just keep in mind, suppose I want to construct information using bits, okay, in some binary language that all of you are familiar, all of you use computers, all of you use mobile phones. So in that, of course, it is inescapable. You use all languages, all machine languages are made of bits, right? So there are two bits, 0 and 1. And just for the sake of expression, for the sake of picturizing, let me label this 0 bit by a red ball, and let me label this 1 bit by a green ball. Okay. So now information has to be created, and information has to be also stored so that somebody else can come and access this information. Now, for example, I create this information 0 bit, and this is a box where I store this information. I open the door of this box, and this is a special box. It has only two doors. One door is on the upside, okay, and one door is in the front. Same with this box. And suppose I prepare a 0 bit and push it down from the one door top here. And similarly, I prepare a 1 bit and push it down from the door on top. Okay. So afterwards, I close this box and go away. And later, somebody else comes and opens this box, and he opens the door. And what does he find? Of course, if you remember, the first box had a red, that is a 0 bit. And of course, if you open the door, you get the 0 bit. And the second box had a 1 bit, that is green ball. If you open the door, again, you get the 1 ball. So this what does it tell us? It is very trivial. And even, I mean, a 4-year-old or a 3-year-old baby will tell you that what went in comes out. Okay. So there is no mystery, right? Okay. So now let us think of a quantum bit or a qubit. After all, quantum bit is nothing but a superposition of classical bits. If you take 0 and 1, and you can make superpositions of them in infinitely many possible ways. How? However, now just imagine that you create a quantum bit, okay? Suppose you create a 0 bit right here, yes, but in quantum mechanics, if you are talking of a 0 bit, that means you are actually attributing to some physical property of some physical particle. Without that, you cannot do. So suppose now you are talking of spin of an elementary particle, spin of an electron, which can take two possible values, either plus or minus, either up or down spin, but you have to define it with reference to some particular direction. So let me say that in this case, I am taking spin labeled by sigma along the x direction, and I am taking spin here along the z direction. So I have prepared a qubit, okay, in quantum mechanics. In this case, I have put again the 0 here, that is the red ball, but I have now this x preparation means that I am using the upper door symbolically, whereas the z preparation means that I am using the front door. So two different doors are symbolically nothing but different ways to both prepare and also measure the quantum state of an atom and photon. So you immediately realize why two doors are important, right? Okay. So now I again repeat the same experiment. I close the box and go away. Now somebody else comes and opens the box. So now, as you see in the first box, if I open the same door, that is, I perform the measurement along the x direction, again I will get 0 along x, no change. Similarly for this box. However, if I do the same experiment, and in this case, in the first box, I open the door in the front, that is, I make although the state was prepared along the x direction, with spin along the x direction, I measure the state along the z direction, then what will I get? I will no longer get the red ball or 0 bit, but with 50% probability, I will get the outcome as green ball or red ball. That is, I will get the 0 bit or 1 bit. Why this is happening? It is again very clear. Because of the quantum mechanical superposition principle, this 0 state in the x basis transforms to a superposition of the 1 state and 0 state. That is pictorially, not really. What happens is that a red ball transforms into a superposition of a green ball and a red ball, and 50% of the time you will get a green ball, and 50% of the times you will get a red ball. So of course, this fact a 4-year-old boy or girl cannot understand. If you try to tell him or her, he will tell you that, see, big brother, big sister, don't show me magic. But after all, this is not magic. This is real quantum mechanics, and this is the profound effect of quantum mechanical superposition principle, and this has profound consequences also. Okay, so let me just come to a very direct, very relevant thing in this that we use in our lives very much. So these days, all of you use Xerox machines, right? You actually, of course, not during the lockdown time, but earlier when the lockdown was not there. So your teachers used to give you papers which you Xerox. Sometimes you take a book out of the library and it is not available in the market or too costly. So you make Xerox copies. So Xerox machine is abundantly available. However, at a quantum level, there can be no Xerox machine. There can be no quantum copier. which is called the quantum no cloning principle, which is a very deep principle. Okay, this is just an artifact, just a consequence of this quantum superposition principle, right? So this is a very profound principle of a very simple physical aspect of quantum mechanics. So what I was talking of is superposition of quantum objects. Now, if you want to think in terms of photons, as I said, photons can have two distinct polarizations, that is horizontal and vertical. So I can label it as 1 by 0 and 1 by 1. And I can do this experiment, of course, with photons here. And of course, there can be infinitely many other possible combinations or qubits. So you can construct a qubit starting from these bits. And for example, this qubit, which actually points in this direction, can be written like this. Similarly for this qubit. Okay, so far I have talked to you about the superposition principle, but the superposition principle was known right since the start of quantum mechanics. But since I told you, this question must come to your mind, that what happened in the 1990s, which actually revolutionized quantum information. Of course, this did not jump at 1990s. The origins were much older. However, the main object of interest, which actually revolutionized our present-day thinking and can do wonders for future technology, is not just quantum superposition, but it is indeed quantum entanglement, right? So what is quantum entanglement? Okay, so quantum mechanics, as you see, is a very successful theory of elementary particles. Now, instead of one particle, so one particle is represented by the wave function psi1. If you have more number of particles, which you can represent by psi2, psi3, so on and so forth. So how will you write the wave function? You will consider the, not just this separately, but you will consider the total wave function of the composite particle. Herein lies the beauty or the mystery of quantum mechanics. Now, suppose you have two different physical entities, A and B, and you want to write down the joint physical state given by one wave function of these two entities. Then, for an entangled state, you just note that it is not possible, so this is not equal, to express this joint state as a direct product of the wave function of psi A and psi B. That is, you cannot express this as a product of, so for example, if this entity represents a particle, this you cannot write this wave function, joint wave function, as wave function of particle 1 product the wave function of particle 2. So this is indeed the meaning in one line, in one sentence of entangled. So entangled systems cannot be expressed like this. Okay. So this is the mathematical definition, but what does it basically mean? Okay, so basically it means something extremely important, very profound. What it means that if you started with these two subsystems and somehow they have interacted and you have constructed an entangled state of these two subsystems, and if they are still entangled, then you cannot individually talk of property of either subsystem A or subsystem B. Individually, they have no meaning whatsoever, right? You can only talk of joint properties of the total system AB. Okay, so this is something which actually evoked a deep mystery in the original forefathers of this subject. So, for example, in the year 1935, Einstein was trying to understand the meaning of quantum entanglement, and this led him to write this famous paper. This is also called the EPR paper. Einstein, along with two of his collaborators, Podolsky and Rosen, and this is historically in the area of theoretical physics. This is one of the highest cited papers of all time. So this paper in Physical Review, those students who are interested, they have a look. It makes a landmark break from classical concepts. So Einstein actually tried to understand this mystery of quantum entanglement, mystery of quantum physics. However, this paper is rather deep, but what I would like you to focus is not the paper, but in fact the interpretation that Erwin Schrödinger made in the following year of what is the meaning of this paper. So what did Schrödinger tell us? The Schrödinger told us, see this blue part, that the best possible knowledge of the whole is in italics, whole system does not necessarily include the best possible knowledge of its parts. Okay, parts in italics. So just ponder back, sit back for 10 seconds and relax and try to understand what it means what it tells us. So if you think classically, then in your room, if you have a table and chair, then you can try to talk of properties of the table and the chair, and you can think the whole room contains both a table and a chair. So if you can understand the chair and understand the table, then you understand the whole room. So there is nothing else in the whole room. However, for a quantum mechanical entity, for example, a collection of 2 electrons, collection of 2 photons, 2 or more photons, or any collection of molecules, if these systems are entangled, then there is no meaning of the parts. Even if you understand the parts separately, this will not give you the best possible knowledge of the whole. So this is a key basic difference in the theory of quantum entanglement. Okay. So then basically the question is that how did all of this come about? It came about by trying to understand what is quantum mechanics. And as many of you know today, quantum mechanics has several postulates. The most common to postulates or important to postulates are the following. One is this time evolution postulate. I already wrote for you the Schrodinger equation. So I'm writing again the Schrodinger equation in this state vector notation. So psi is the state vector, h is the Hamiltonian, say h the time evolution is given by the action of the Hamiltonian on the quantum state. So this gives you the evolution of the quantum state from one point of time to another. However, a quantum state may evolve by itself without an experimenter or a measurer doing anything. It keeps on evolving. But as soon as an experimenter wants to extract some information from the quantum state, then he has to perform a measurement on the quantum state, right? And as soon as you perform the measurement on the quantum state, the laws of quantum mechanics become completely different. So they are no longer described by this unitary time evolution, but on the other hand, they are described by something which is called the reduction postulate or collapse of wave function. So what is the reduction postulate? Suppose you are trying to measure an observable P, which can be position, momentum, whatever. So now initially your state was in a superposition of eigenstates of this observable P. So I can write this psi in a superposition of this eigenstates of observable P with coefficient Ci. Now you make a measurement, and what happens is that one eigenvalue given by lambda k gets projected out, which occurs. So as an outcome of the measurement, you observe only one eigenvalue. Okay. And what you get is the end state becomes this eigenvector. Okay, phi k. Not a superposition of all possible basis states, but an eigenvector. So what is happening initially, your state was a superposition, and after the act of measurement, it goes into one particular state. So this is a completely non-unitary evolution. It is a sudden jump. It is completely different from Schrodinger unitary evolution, and it gives you a single outcome. So point is, what is in the theory that is giving you a single outcome? So is it possible to discuss the projection postulate not separately, but also within the quantum formalism? So this is a great problem which was posed by the forefathers of quantum mechanics, and there were several attempts, several methods to answer this question. All of us gave rise to even greater or profound mysteries. Okay, and one of them is the quantum measurement problem that will very briefly describe to you. Of course, this is a very deep problem, and there is no solution even after 100 years of quantum mechanics, or at least 95 years of quantum mechanics. So what does this tell us? This tells us, suppose you have an initial system in a superposition of some eigenstates, and you have an apparatus which is also I'm labeling by using a quantum mechanical vector notation. After all, an apparatus has to be by definition classical, since you want to note and record an observed value. However, let me for a moment try to label it or try to describe it quantum mechanically. That is the whole idea. Okay, whether I can describe you the reduction postulate quantum mechanically. So now, when your system interacts with the apparatus, I can write the joint wave function like this. And since it has interacted, they are not separate, so they combine together and unitary evolution takes place. So the whole system no longer is a product system, but it turns out to be a superposition of these combined states in some joint system apparatus basis. Okay, and of course the interaction occurs through some physical means. Say they have some system, some interaction Hamiltonian, apparatus system interaction Hamiltonian, which operates for a short time. And what is the end result of that Hamiltonian? This initial superposition goes into a final superposition, because after all, again, Hamiltonian causes a unitary evolution, right? So finally, again, you see what happens is the final state is an entangled. You remember the definition of entangled state. It is not a product state. So the final, what we are getting is an entangled system apparatus state as a final state, but we are not getting a single outcome. However, this is completely contradictory to common sense and logic. So any experimenter who has done any experiment will tell you that if he measures anything, he gets a definite particular outcome. How do you observe an outcome? You suppose you measure some current or some property and you see some meter. So you will see the meter actually taking a particular reading. So never you can find that after a certain given time that the macroscopic pointer is actually oscillating. So a particular single outcome of position or momentum is obtained. But your theory is telling us that there will be a superposition. So therefore, even if you try to measure model the apparatus quantum mechanically, you will end up into many problems. And there were many similar mysteries or paradoxes at the beginning of quantum mechanics. As soon as you try to, you actually try to describe macroscopic objects like apparatus using quantum mechanical laws, you turn up into paradoxes like the Schrödinger's cat, Wigner's friend, so on and so forth. So again, this is a description of the mysterious Schrödinger cat experiment. So I will not have time to go into this, but if anybody is interested, I will be happy to describe it at the end of the talk. But my purpose of this to tell you this, that actually quantum foundations lead to a lot of many different mysteries, and in order to understand them, that is why we have come to this stage. The theory of quantum information has been developed. So the point is, how does a classical world emerge? So this is one of the deepest mysteries. So all elementary objects, microconstituents of the classical world, obey quantum mechanical properties, but they have counterintuitive features. But whenever we deal with familiar objects, they behave classically. So what happens? So this is one of the very deep challenges modern physics is facing. But today's focus is on something else. So what is, by the study of such challenges, what new things have come up? So I was previously talking of in 1935, that is the EPR paradox. So now let me take a jump of 30 more years, go to 1960s. So in 1960s, there was a physicist called John Bell, and he made one of the most profound, suggestions or discoveries. And what did he do? He was a mathematical physicist. He actually proposed some mathematical inequalities, which are known as Bell inequalities. And they actually captured this departure from classical features that entanglement brings. Quantum entanglement brings about a profound departure from classical properties. So how do you quantize or quantitatively discuss such departures? So that is given in terms of Bell's inequalities. Okay, violation of local realism. So again to sort of summarize, how does entanglement arise? Suppose you have a source which emit two particles going to two different sides, and because they are emitted from a common source, their joint wave function psi AB cannot be written as a direct product of individual wave functions on both sides. And in actual physics, you have by now come across many such examples. For example, you have heard of singlet states, triplet states of two spin-off particles. They are given by this. Okay, so these states are nothing but some maximal examples of maximally entangled states, and there can be many more examples of entangled states. So again, what am I trying to say here is that suppose we have two non-interacting systems. That means the system may have interacted in the past directly or indirectly, but now at the present moment they are not. interacting. So I can take the state of this composite system in a general basis. And if I do an example of two basis vectors that can describe for you not only spin of electron, but also polarization of photons, then I have this most well-known ubiquitous example of maximally entangled singlet state. By the way, what does it mean? Okay, so suppose this is an example of a singlet state, entangled state, and A means an observer, a particle on one side, B means observer for another particle on the other side. So now suppose observer A makes a measurement on his particle. Any single observer only has one particle, because after all, there are just two particles. One is with one observer, another with another observer. So if one of the observers, let us say A, makes a measurement and he gets, say, 0, meaning horizontal polarization on his side, then what does it mean? Then it tells us that this part in the superposition, only this part of the state, the first term is projected out. That means whatever happens on the other side, if the other side observer makes a similar measurement of polarization on his side, he will definitely get a 1 polarization, right? He will not get a 0 polarization. On the other hand, if the observer on the left side gets 1, then because this part of the wave function, after all, even probabilistically, any observer on one side will get 50% of the time 0, 50% of the time 1. But on that occasion, which he gets 1, then the observer on the other side is forced to get the outcome of the occurrence 0. That is the whole whole mathematical structure of this entangled state. So what does it mean? It means that two particles which are entangled have this ability to, first of all, acquire and also retain correlations, because at this point of time they are no longer interacting, but they retain correlations in their physical properties even if they move far away from each other. So that is very important. They retain these characteristic correlations even if they move far away from each other, and it is indeed these correlations which can help us to make such entangled states, to use such entangled states as resources. Resources for what? Resources for performing many very interesting protocols. Okay, so that is the modern end perspective of quantum entanglement. So in 1990s, first applications of quantum entanglement in information theoretic protocols were given. And what are the most famous information theoretic protocols which you cannot do without quantum entanglement is quantum teleportation, okay, some forms of quantum cryptography, quantum dense coding, and also some forms of quantum computation. Okay, so in one talk it is not possible to go into all details, but I will at least try to give you some flavor of one or two of these things. So let me start with quantum cryptography. Okay, so basically what is cryptography? Cryptography means hiding some information from some enemy or adversary. Like, for example, all of you use computer accounts, all of you use emails, etc. You give a password in your email. Why do you give a password? Because you do not want somebody else to come and read your own emails, which you can think is secret. And what is basically a password? Password is a combination of letters, right, numbers, or even special characters which you can find on your computer keyboard. Okay, so now you make a combination of 6, 7, 8, or maybe 10 such characters, and you make a password, and these are difficult for anybody to crack. But now suppose you imagine that some hacker has a computer with him, and using that computer he will try to hack your password. So is it possible? It is very much possible, because after all, what a computer will do, it will just take one by one all elements on the keyboard and make combinations one after the other, and after a given time, depending on the speed of your computer, he or she will be able to hack the password. So this is a hallmark of all passwords which are set up using classical laws of physics, that nothing is absolutely secure. However, on the other hand, if you use quantum mechanics to make passwords, or you use quantum cryptography, then you can make your passwords, I mean, not only passwords, but you can make any information completely secure in principle and secure from fundamental principles. So that is the whole point. And this thing has been used, quantum cryptography, already been used in many different areas. For example, another area which it has been used in is in electronic voting machines. Okay, all of you are familiar with voting in our countries. So when elections take place, voting takes place, and voting takes place maybe through ballots or maybe through machines. But in our countries, what happens is that if I lose, I will accuse my opponent of actually rigging the elections. I will say that no, the opponent actually rigged the voting machine. So whatever button I press, I only end up voting in favor of my opponent. So can we make this completely secure? Answer is yes and no. Using classical laws of physics, you cannot make it completely secure, but using quantum mechanical laws, you can make it completely secure, as indeed it has been demonstrated in Switzerland elections in Geneva using quantum cryptography. Of course, Switzerland is a very rich country with very small number of people, but they have indeed done it. Okay. So basically, what is the physical idea? Physical idea is any secrecy or privacy is founded on principles of fundamental physics. So here there is a cartoon. So Alice is trying to send up some information to a Bob who is far away from Alice, but maybe the information is over a telephone or an optical fiber or whatever, but in the middle there is some evil person or eavesdropper or hacker called Eve, he who wants to hear or wants to find out what information Alice is sending to Bob. So as I said, so whatever classical, by means, if you say send classical information, then if Eve has access to a powerful computer, Eve will always be able to know the secret between Alice and Bob. However, in quantum cryptography, privacy is founded not on the assumption that eavesdropping requires difficult computation, not on the fact that you mumble, jumble up many different types of characters and special keyboard characters, but it is founded on principles on fundamental physics. Okay, and what is the fundamental principle? It is the quantum uncertainty principle. So all of you should know by this time, what does this quantum uncertainty principle tells us? That if you try to measure a system, you impose a disturbance of that system, and after that this disturbance of the system, your original state is no longer your end state, your final state is no longer the original state. So you not only impart an unavoidable disturbance, but you also impart an uncontrollable disturbance. For example, if Eve wants to measure the state, she imparts an uncontrollable disturbance of the state, and therefore Alice and Bob will know that this state has been disturbed by the eavesdropper. They will throw away the key and they will use another key. So this is the principle of cryptography, and the cryptography was first invented by these two famous people, Charles Bennett and Gilles Brassard, in 1984. So this was a theoretical development, but today you already have some QKD machines for sale. So there is a company called ID Quantic in Geneva. So you can look into the internet and you can actually order these systems. And not only that, I'm happy to tell, even in India, there is now a company in Bangalore which has started making some not so sophisticated versions of QKD machines, but at least some QKD machines which will be commercially available soon. So this is something which is practically possible. Okay. And similarly, I mean, I think also most of you have known that quantum computers are something of the future. So even when quantum computers will come, they will totally revolutionize how you do computing at present. And again, here laws of quantum physics is used, basically the power of parallel processing. As I said, that you do not have, so classical computers use these bits 0 and 1, but a quantum computer will use these combination of bits, the infinitely many possibilities all together, all parallelly. So they will become profoundly more powerful. So for example, this is a picture of more than 15 years ago. So at that time, people thought that if you can build a quantum computer at various frequencies, okay, so more the frequency, more powerful it is, more parallel processing it can do, then you can handle larger and larger bits at the same time. So this is on a logarithmic scale. So classical computers develop like these graphs, okay. So if you want to handle more and more and more and bits together, you need more and more powerful computers. So for instance, in 2003, 104 PCs were able to reach this state, whereas in 2018, 100 PCs are able to reach this state, okay. And slowly, as soon you will see that on y-axis you will have the age of the universe. Again, it is in a logarithmic scale. So the classical computers have reached a roadblock. You cannot do much more important. However, if you are able to make quantum computers, then you will completely overhaul this roadblock, and you can harness the immense power of the quantum. Okay. So for quantum computers, this much, and let me try to actually come towards the end of my talk by talking about this again, this very so-called mysterious element or effect of quantum teleportation. So what is quantum teleportation? So in a quantum teleportation, the idea is that on one side, you have a quantum state here, and your purpose is to actually transform or to send the state to other side which is far away. Of course, you cannot physically send the state there, but you can send some information on the other side by which, so if your friend is here on the other side, using your information, he or she can reconstruct exactly the original quantum state, right? So how does it happen? So this is not science fiction. It happens in practice. It happens in the following way. So these two sides, for example, Alice has a quantum particle. Similarly, Bob has another quantum particle. However, what is more important is that there is some other agency who prepares an entangled pair of quantum particles, who prepares two more quantum particles which are entangled and sends one of them to Alice, the other to Bob. Now, what Alice does is to combine his original particle with one of the entangled pair and do a measurement. And after the measurement, Alice will get some data, and the data is sent to Bob by standard means, by optical fiber, telephone, or whatever. And using the data, what Alice will do, he will have access to the other particle of the entangled pair. He will, using the data, depending on that data, he will apply some treatment, and at the end, lo and behold, what you will have is the exact replica of the original particle. But remember, those of you who listened attentively to my talk, in the earlier slides, I told you that there is no quantum copying, there is no quantum cloning. So what is happening here is that the original state with Alice is completely destroyed. So this is the charm of quantum teleportation. So this is nothing but replication of an unknown state. By the way, the original state, Alice also does not know what the state is. So this is replication of an unknown state at a distant location. So this is not only possible mathematically using quantum entanglement, but this is actually physically possible. This is no longer science fiction. People have done experiments, and photons have been teleported at the distance below Lake Geneva at the length of more than 1,000 kilometers. And not only that, our neighboring country, China, has actually claimed of doing teleportation between the Earth and satellite, which actually orbits in space. So this has been completely done so far. Now, if you ask what is the use of this, of course, it is fascinating scientifically, but it will also have very great practical use. When you actually make teleportation happen practically, then by this process of teleportation, you can combine many different resources. For example, if you have one computer in Pabna and I have another computer in Kolkata, then by doing teleportation, I can combine our two resources and do a fantastically secure computation extremely securely. Nobody else will be able to know what we have done. So this has many profound applications. Okay, but let me again tell you, so far practical teleportation we have been able to do, or experimenters globally have been able to do, only using 1 or 2 particles. We are far away from the science fiction stage, whereby we can actually say teleport, I mean, even a large ball, or just forget about, I mean, cats or dogs or human beings, certainly not, but at least small particles we can indeed teleport. Okay, so just to have the meaning of teleportation, what is the task of teleportation? What are the salient features? The task is to transport an unknown state of a quantum system to a distant location, and the most importantly, it has to be done using the resource of an entangled state that is shared by 2 distant parties A and B. And the protocol is party A makes a measurement on the system to be teleported. Party A then transmits through a classical channel information to B, and party B makes a transformation on the system which is located with him. And what is the result? What is the outcome? The true copy of the original system, which was initially at A, is now transferred to B. Okay, location B. Original system at A is destroyed, and this is very important. System A is not physically transported from A to B. So you have to remember that. So again, this is again, I mean, taking too deep into research. Maybe I should not go into this, but just to tell you what I'm saying is just not something airy-fairy or just not some storybook reading. Indeed, there is a lot of research which is going on in this area. For example, something is very important is the idea of entanglement weakness. What is entanglement weakness? As all of you know, quantum entanglement is a useful resource for performing many tasks that are not achievable using laws of classical physics. For example, teleportation, dense coding, etc., etc. Now, the question is, suppose somebody actually creates 2 particles have interacted. How can you be sure that they are indeed entanglement? Or in other words, for a practical person who is an experimenter, who is in a laboratory, how can he or she detect whether 2 electrons or 2 photons are entangled? So you can also reframe this question. So if you have an unknown state which somebody else has prepared and you want to use this state, say, for performing any task like teleportation, so can you tell, will it be useful for information processing? So how do you find out? So the method again comes from quantum mechanics. In quantum mechanics, we know that Hermitian operators are observable. So if we can measure some Hermitian operator on the given system of 2 or more particles, and the measurement outcome gives you some expectation value which tells us the character of the state, whether or not the state is entangled, then we can actually, doing that measurement, we can determine in the lab itself whether an unknown state will be useful for information processing. Right. So this kind of witness can be used for detecting many interesting tasks. For example, one can ask this question, whether a given state is useful for teleportation, and if you have an unknown state, then what will be the quantum fidelity? By the way, I should tell you that after all, any process is done with some errors. So whenever the process is completely error-free, we say it has 100% fidelity. Otherwise, we define a mathematical object and calculate the fidelity. So similar question can be asked about the purity of states. I did not tell you what a pure states are, but just take this much. So in any given state of particles can interact with other particles which form the environment. And as soon as we lose knowledge of the other particles, then the state can no longer be described by using just state vectors. We have to use the density matrix formalism to describe the state. So then the state is no longer pure, but it is mixed. So this is also a practical question because you cannot make any system completely free of its environment. So in a given system, you have to answer such questions like how far the state is mixed, how far it is pure, so on and so forth. Right. So actually, I will just end that by saying that this subject of witness for teleportation was a very modern subject and interesting subject. And our group at SN Bose National Center for Basic Sciences and indeed done some very useful work for the last 10 years or so on quantum teleportation. For example, 10 years ago, we indeed answered this question, how could we know if a given state is useful for teleportation? And we used the concept of teleportation witness, and this was published in Physical Review Letters, which is brought about by the American Physical Society in the year 2011. I, along with two of my ex-students and another collaborator in Heritage Institute in Kolkata, we proposed this idea of entanglement with witness operator for quantum teleportation. So our group at Bose has since then done many such works on this quantum teleportation. So this is a very interesting and a challenging modern area. So this was just to give you an idea of some kind of works which we are doing at Bose. So now finally I have come to the conclusion or summary of my talk. So what basically I tried to motivate you in this talk is how to develop the area of quantum information. So an essential property of quantum mechanics is the superposition principle, and this helps us to go from classical bits to quantum qubits. Of course, the most important property of quantum entanglement then comes and then is taken into account. And this is a special property of physical systems. This is clearly manifest at the microscopic level. If you want to see this property at the macroscopic level, you have to do extremely hard work, which is also challenging, and it is one of the areas of modern research. Of course, so this entanglement has brought upon the possibility of performing entirely, categorically, and fundamentally new and interesting and useful tasks through the use of quantum entanglement. And this has it has ushered in the prospect of a second quantum revolution. By that I mean all these things, teleportation, cryptography, computation, have been demonstrated in the laboratory, but now the challenge for the future is to make it accessible to the mass, to a whole range of population. That is the challenge for the future. And of course, this is not just a sort of technological challenge, this is also a theoretical challenge, because as I have tried to emphasize right at the beginning, this area is very intimately connected to some very deep-rooted physical and mathematical problems or puzzles in physics, mathematics, and computer science. So basically, they are summed up by understanding of quantum non-locality. So for example, if you are a young student, you want to take up this subject, the road ahead is very fascinating. There are at least 20 different very challenging areas. So I have just listed 3 or 4 for you. So you can see, for example, if you have multipartite systems or large systems, how can you quantify entanglement? So for example, if you want to teleport larger systems like buckyballs or carbon atoms, they are made of multiple particles. So how do you quantify entanglement? As I said, there are fundamental problems of understanding. How do we understand quantum non-locality? How do we understand quantum measurement problem? Then indeed something which is extremely practical, important is that this so-called environment, this action of environment, which leads to decoherence or destruction of entanglement of quantum particles. If you want to harness the power of the quantum, you have to control this decoherence. And this is the biggest challenge in our face of realizing quantum computers. So this is one of the biggest problems. Then within the field of quantum computers, of course, there are many interesting algorithms. And those of you who are interested, those of you come from a mathematical background or quantum or computer science background, must already know about Grover's algorithm, Shor's algorithm, Deutsch-Joshua algorithm, so on and so forth. But if you try to read, you will try to see how ingeniously people make use of the power of quantum parallelism. And there are many others, so on and so forth. And finally, I will end this with this slide, which is a pictorial slide. So many different areas, very interesting research is going on worldwide into this realm of quantum science and technology. First of all, you have to ensure secrecy in all quantum communication tasks. You have to ensure secrecy. So this point of view of quantum secrecy, quantum communication. Then there is quantum hardware. You develop quantum computers. On the mathematical side, there is a lot of work in developing suitable algorithms for quantum computers, so on and so forth. There are many different areas, and all of these leads to some very nice challenges for basic physics. So I would like to end my talk with this. Thank you very much. And now I open the floor and welcome you if you have any questions. Thank you. Thank you.
Thank you, sir, for your wonderful presentation, sir. I think students have learned a lot of things, and you have explained the quantum mechanics and its application very well. So if you allow, we can start
Yeah,
our
please,
discussion
please.
session, sir. So we have
Yeah.
already got some questions. So first question in inbox. So what is uh, quantum key distribution, and why quantum cryptography is important?
Yes. So I will come to you once again. So basically, forget quantum. What is key distribution? Key distribution is trying to make a secret key of something, like a secret password. I gave you an example. So if I combine, suppose I just talk of binary example now, I use the bits 0 and 1 to construct a bit. So for example, 00010101. I make this bit. Okay. So now using this bit, I share it with myself and you, because I want to send you some hidden information, and using this key, you can uncover this hidden information. That is the purpose. Now, if there is some eavesdropper or hacker, if he or she gets access to this key, then this information will no longer be hidden. Now, what will the eavesdropper do to get access of this key? Eavesdropper, in this simple case, will just run a computer program. It will give him many choices, say for example 00000101. So he will keep on making permutation and combination, and ultimately he will get access to this key, right? But if your key string is not from classical bits, but it is made using quantum qubits, say superposition of 0 and 1, as soon as the eavesdropper wants to want to learn about this key, he makes some measurement on the quantum particle, and due to the quantum uncertainty principle, he or she imparts some uncontrollable disturbance on the key. As soon as this disturbance happens, I and you will get to see that there is somebody who is trying to hack our password. So we will immediately change this password. So in simple language, this is quantum cryptography. But after all, it is in actual practice, it is very complicated. It uses features of quantum superposition and in some cases quantum entanglement, and using that, practically some machines have indeed been constructed. Okay, I hope this answers your question.
Thank you, sir. There is another question in the inbox. So what is quantum teleportation, and is there a relation between telegraph?
Okay, what is quantum teleportation? I just
I think you have explained.
I have come to slides. Let me just come back to this picture. I'm not going full screen, but I hope this picture is you can see it. So basically, the task, as I said, that suppose you are here and your friend is on the moon, for example. Okay, or let us talk more realistically. You are here and your friend is on the satellite. Okay, you can send people on satellite. You know that is possible, and this satellite is a military satellite. Let us take this example. And you are sending your friend is going around the globe, and your friend is making some picture of some enemy country, and your friend wants to send this picture to you. Okay, so this is a very real task, but you want to make sure that your enemy is not able to actually see this picture, right? So how can you do it? Of course, your friend will use radio communication from the satellite to you, but your enemy will again try to intercept this radio communication, so enemy will be able to find out. But if instead of simple classical transmission, I'm using radio waves, I'm calling that classical transmission, but if you apply quantum entanglement, you accomplish this task again using an entangled pair of objects. Then your communication from satellite to ground on Earth will be secure. So teleportation is a process by which we send information about the quantum state of a system to a very far away location using the resource of quantum entanglement. So this in one line is quantum teleportation. However, the whole protocol takes place by application of several unitary transformations and measurements. So you will have to study this area of quantum entanglement and information in order to understand this system thing.
So thank you, sir. This may be the last question. So what is the key difference between the classical algorithm and quantum algorithm?
Yeah, the key difference between classical, so algorithm, if you are talking in terms of quantum computers, then you can, of course, so far in all things we do up to date, I mean, all of us, we use classical algorithms in computers. Why? Because our classical computers are programmed in such a way that they work on the principle of bits, 0 and 1 bits, using combination. So all your algorithm you type in some language, they are transformed to machine language, and the machine language understands bits, right? 0 and 1. But now when you want to do quantum algorithm, you are not just restricted to zeros and ones, but you can use a combination, you can use a superposition, infinitely possible many superpositions. So therefore you can do parallel processing in such a way that is not imaginable in classical computers. So for example, to give you an example, so say let us talk of Grover's search algorithm, right? So you have a collection of numbers, say from 0 to 100 or whatever, and you want to find out, you want to pick up a particular algorithm. So using a a particular number. So using a classical computer, how do you start? You start from one side, you can start from the 0 side and reach to that number, or you can start from the 100 side, come down and reach to that number. So approximately, on average, how many trials you will need? You will need n by 2 or linear n, right? So this is a classical algorithm. You will need so many trials. But as soon as you harness the power of superposition, if you do Grover's search algorithm, then you will not need a linear number of trials, but you will need a square root of n number of trials, which on average is much lesser, much faster than a linear number of trials. So as soon as you go to higher and higher numbers, you will appreciate the beauty of quantum parallel processing using quantum algorithms. So this is just one algorithm of search algorithm. There is many example, prime factoring example, Deutsch-Josa algorithm, many others. So okay, Schrod's algorithm, many others. So on and so. Yes.
So thank you, sir. As there is no more questions, so we can conclude our discussion session, sir. So thank you, sir, for your wonderful session. And I'd like to inform you that we have celebrated our 50th webinar to dedicated with Dr. Our respected scientist S.N. Bose, sir. So we can show you the poster of that 50th. So as you belongs to S.N. Bose Center, so this was our 50th. So we celebrated on 27th of September. So thanks, sir, so for accepting our invitation. So we would like to say thanks on the behalf of the Department of Physics. And this is very interesting and exciting talk with you, sir. And I hope our students have benefited lots. So thanks again, sir. And hope in near future we will again another webinar with you, sir. So bye for today. See you.